So our next topic here, we just talked about how to draw Lewis structures. Then we talked about what shape those things take on using Vesper theory. And the next thing we're going to talk about is how do they interact with each other? How does one molecule interact with a molecule next to it? And it turns out to understand that, we have to understand how the electrons are distributed within the molecule. Because remember, pretty much all of chemistry has to do with electrons. These electrons repelling these electrons, or this part being attracted to this part. All has to do with the electrons, because when you come up to an atom, what do you see first? You see his electrons, not his nucleus way back here. And so all of our stuff is going to be coming up with electrons. So it turns out that when we talk about covalent bonds, we're talking about sharing, right? We draw this thing that says, oh, we've got a carbon bonded to a chlorine. We say we are sharing this pair of electrons right here. Well, is all sharing equal? And the answer is no. So if you look at maybe, I don't know, a 2-year-old playing with a 6-year-old, and they're sharing a toy, is it really equal sharing, right? If no one's watching, chances are the 6-year-old's going to try to play with the toy a little bit more than the 2-year-old because he's bigger and stronger. Atoms do the same thing with electrons. So chlorine and carbon, even though they're sharing that pair of electrons, and they really are sharing it. No one's taking it, no one's giving it away. They are sharing it. But it turns out they're not sharing it entirely equally. Chlorine doesn't share as well. And if he doesn't share as well, and we've got this electron floating around, so I'm going to draw this kind of electron floating around between them, and it floats around carbon, it floats around chlorine a little bit more often than carbon, a little bit more often on chlorine, a little like that, right? If we start to look at this drawing here, and it's not the best drawing in the world, but right, chlorine has the electron more. So if we look, it kind of looks like chlorine has the electron. I mean, carbon's got a little bit of red on it. So if it's not equal sharing, what is it? Well, it's unequal sharing. It's not giving away. It's not ionic. Remember, ionic is a metal and a non-metal, and one of them's giving it away and one of them's taking it. That's not what's going on here. Chlorine just has it a little more than carbon does. So he's not like negative like he is in sodium chloride. NaCl, chlorine is negative. He's chloride, he's got that electron. But here, he's got it a little more often. So he's a little negative. And what we do for little is we use the Greek letter delta, lowercase. So it looks like an S that you kind of curve onto itself. And we say that chlorine is a little bit negative because he has the electron a little more often. Well, carbon has the electron a little less often, so what is he? He's a little positive. Remember, if you don't hang out with those negative people in your life, you become a little more positive. So carbon is a little bit more positive. And what we have here is still a covalent bond. They're still sharing. But now we call it a polar covalent bond. They're sharing unequally. And what's really cool about this is I'm going to start drawing up in the corner here. If we've got a C bonded to a Cl, and this guy's a little bit negative, and this guy's a little bit positive, what happens when you come up to another guy, and you've got a chlorine over here, and a Cl over here, maybe in another molecule next door, and you've got that little bit of negative, and that little bit of positive, all of a sudden, these two molecules that aren't actually bonded to each other are going to attract each other. Positive on one carbon is going to be attracted to chlorine on the other carbon that's negative, or on the other molecule that's negative. And these molecules are going to start interacting with each other and doing cool things like chemistry. So how do we know who wins? Well, it turns out there's a few different ways. The most standard common way is to look at a table. And you look at a table like there's one in your textbook, and it has all these numbers on it right here. Like if we look at fluorine, it says 4.0. And what these are called Pauling electronegativity values. The bigger the number, the more an atom likes to have electrons. So we just introduced a new term, electronegativity. And that is the tendency of an atom to attract electrons. I'll use E- for short. And here, since we said carbon, chlorine likes it more, we say chlorine has a higher electronegativity than carbon does. Windows thinks it's time to restart, even though I'm in the middle of something. Isn't that fun? And we can actually see that if we look up on this table. Chlorine over here has a Pauling electronegativity of 3. Carbon has one of 2.5. And so chlorine wins. Right? Another way we can do that is here we use the delta plus and the delta minus, the Greek letters. But it turns out people also do things where they draw an arrow to the winner. and then sometimes put a little plus sign on the sign of the thing that's a little bit positive. So we'll do both. We'll sometimes draw the line and sometimes use the deltas. Okay, so how do we know who's more electronegative? One way is just to look at this table. And then it turns out if two atoms are bonded to each other and their electronegativities are different enough, so if you look at chlorine, it's 3, carbon, it's 2.5, 3 minus 2.5 is about 0.5, we call that a polar bond. That's kind of the traditional way. I don't generally teach that way because I don't really like having to look up numbers in a table. So what I do is teach a little kind of a different way. It's not anything you're going to find in a textbook. So if you're looking at this video and you're in another class, you might want to ignore this part. But it's actually a really practical way of talking about it. And what I teach is this, that all bonds are polar. Now, Professor Clements, are really all bonds polar? The answer is no, because this is chemistry. And on chemistry, there's always exceptions. So except for the following. C bonded to H, C bonded to S, S bonded to H, and anything bonded to itself. Right? If chlorine's bonded to chlorine, nobody's going to win. Okay? I've had students in the past tell me that they remembered these ones as cheese, right? C, H, and S. Any combination of those, that's not going to be polar. C and H, they share very, very well. S and H, they share very, very well. Nobody's dominating. Okay? And again, anything bonded to itself. So you can look at a bond and be like, oh, well, if I've got, sulfur bonded to bromine, you could go look up in that table, oh, let me look what it is for sulfur, subtract it, figure out, oh. But, in my world, it's not on that list. It's not cheese. Therefore, it's polar. And it turns out it acts polar. Carbon bonded to iodine. If you actually do the official thing, it comes up as nonpolar. But in organic chemistry, carbon bonded to iodine acts as a polar bond. And so I'm going to call it a polar bond. Again, I get slightly different answers than the traditional method, but it's more of a practical one. It acts like a polar bond when it does chemistry. Okay? Now, how do we know who wins? This just tells us whether it's polar or not. How do we know who wins? Who's going to be the negative? Who's going to be the positive? And it turns out to matter. Well, you could look up at the electronegativity values. I just remember a little acronym, FOCL, NBR, ISC, Focalin-Brisk, FOCL, NBR, ISC, Focalin-Brisk. Fluorine, most electronegative thing on the table. Anybody who competes with him loses, other than fluorine. And so the closer you are to fluorine, the more likely you are to win. Anybody off the list is beaten by anybody on the list. So if we go back up to our carbon iodine up there, iodine is over here. He's closer to fluorine, so guess who wins? The iodine does. Sulfur and bromine, bromine's closer, so guess who wins? Bromine does. Okay. What about if we had like an H bonded to a Cl? Who's going to win there? Chlorine on the list, hydrogen not on the list. Chlorine's going to win. Unless you think it always points to the right, I can draw an O bonded to an N. That's definitely a polar bond. And who's going to win? Oxygen, because he is closer to fluorine on this list. Okay? So Focalin-Brisk is how I remember it. But again, you could look up the electronegativity values. They will not be given to you on a test. All right, so now we know who wins. We know how to determine whether molecules are polar. And part of the thing is, why do we care? And again, it's because one polar part on one molecule can start to interact with a polar part on the next molecule, and that'll change its properties. All right. So we did that. We did that. Now, that's polar bonds. We're just looking at two atoms. When you're talking about a bond, it's just two atoms. This atom bonded to this atom, is that polar or not? But that's not what molecules are made up of. Molecules are made up of lots of atoms. Right? So we did CO2. Looks something like that. We did COH2. Looks something like that. We've got H2O. Looks something like that. If you remember, the shape of H2O was bent. Right? So we're not just looking at single bonds, right? We can, right? This C bonded to O, that's a polar bond. Oxygen wins because he's closer to fluorine. This O bonded to H, that's a polar bond. Oxygen wins because he's closer to fluorine. This CH bond is a non-polar bond. It's part of cheese. Okay? So nobody wins, so we don't have to draw an arrow there. Okay? So how do we look at it when it's all together? Well, when I do this in class, I have two people come and they stand. And do I have anything? So here's CO2 right here. Right? We've got the carbon in the middle, the two oxygens on the side. Now, what I'm going to do is I'm going to pull on it to talk about polarity. So if I've got my hand in the middle here, and I've got a polar bond on this side, it means I'm going to be pulling this oxygen. This oxygen is pulling the electrons, and so my molecule would move. Right? But let's look at this other side. Well, this is also a polar bond, right? This carbon attached to this oxygen. And if I pull it, it would move this way. So what I have is I have somebody pulling this direction and somebody pulling this direction. And lo and behold, if I pull on both of these at the same time, nothing happens because they're balanced out. One pull is canceled out by the other pull. So even though we've got a polar bond pointed this way and we've got a polar bond pointed this way, when they add up, nothing happens. And so CO2, we say, has polar bonds. Right? It's got two polar bonds. They're C bonded to O. They're both polar. The oxygen wins. But it is a non-polar molecule. Wow. Because when you put it all together, it all cancels out. When you look at it from really far away, you don't see it moving one direction to the other. Now, it doesn't actually move, but that's the analogy we can use. Right? You don't see those electrons sitting on one side more than the other when you look at it from really far away. Well, what about this molecule? This molecule, this one right here, these guys are not polar. Right? There's nobody pulling this direction. There's nobody pulling this direction. There's only somebody pulling this direction. And so what do you see? If there's only somebody pulling this direction, is everything balanced out? It's not, right? Because we're pulling up constantly. We have this polar bond that's a C-double-O, so we do have polar bonds in this molecule, which is the C bonded to the oxygen. The oxygen wins. And this is also a polar molecule because, well, there's only one pull in one direction. So we have a polar molecule. Alrighty. What do you think about water? Well, it turns out when you're looking at these things, trying to figure out whether something's polar or not, you have to look at the entire shape. You have to actually do the Vesper theory to figure out the shape. And you remember, water is bent, so it looks like this. Right, and I've got water here. We've got O and H. Oxygen wins, so there's something pulling in this direction. We've got O and H, there's something pulling in this direction. So the left and right actually balances out, but the top doesn't, and it goes up. And so what you have is polar bonds with a polar molecule. In fact, water is one of the most polar molecules we know of. Cool, so we can determine whether molecules are polar, not just atoms. Now, turns out if you want rules, because rules are fun, they're this. Rule number 1. If there is a lone pair on a central atom, the molecule is polar. Turns out those lone pairs really mess with things. 2. So if you find out it's polar, you stop there. If there are no polar bonds, right, all you have is cheese. Carbon bonded to hydrogen, carbon bonded to sulfur, sulfur bonded to hydrogen, or a bunch of things bonded to itself, then the molecule is nonpolar. And lastly, if there are polar bonds, right? So again, if you decide it's nonpolar, you stop there, you don't go on to the next rule. If there are polar bonds, then you do snap, which means if the molecule is symmetric, it is nonpolar. And if the molecule is asymmetric, which means not symmetric, it means polar. Right? S, N, snap. So let's do this one as an example. Now, it turns out these are all nonpolar bonds, but because they're carbon-hydrogen. But let's say they were polar bonds. How do you know if something is symmetric? Well, if you look at this molecule, I've got it like this. Now, close your eyes. Open your eyes. Did I rotate it? Can you tell? Okay, close your eyes again. Okay, did I rotate it? You can't tell. That's a symmetric molecule because everything looks the same no matter which way you look at it. Now, on the other hand, if I were to take a very similar molecule and I just have this blue dot here, you're like, well, it looks kind of symmetric like this. But it's not completely symmetric because if you close your eyes and you look again, did I rotate it? And you're like, yeah, the blue thing was on top before, now it's in front. And that's an asymmetric molecule, so this would probably be a polar molecule if it had any polar bonds. Chances are that's a polar bond. Okay? So that's how we use it. If you can turn it around and there's pretty much no way to tell the difference, then it's a symmetric molecule. Okay? And again, why do we care about this? We care about it because it changes the properties of it. Let's look at CO2 and H2O. Right? When does water freeze? 0 degrees Celsius. When does CO2 freeze? You're like, I don't know. I've never seen CO2 freeze. Yes, you have. Dry ice. Dry ice is really, 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 really cold. Okay? Why? And then dry ice turns into gas right away. Right? Let's even think of room temperature, right? Gas at room temperature, liquid at room temperature. Why? Well, liquid means they want to stick together. Why do they want to stick together? Because water is a very polar molecule. When you have these hydrogens over here, and you've got this negatively charged oxygen, slightly positively charged hydrogen, when another water molecule comes by with its slightly positively charged hydrogen, he's going to interact with that negative oxygen there, and they're going to be kind of attracted to each other. They don't want to leave each other. And so you get things that, well, I've got to put a lot of temperature in. I've got to really force these guys to go away. Well, that's boiling. So if we want it to boil, we've got to put in a lot of temperature, a lot of energy to get them to separate from each other because they don't want to. But what about CO2? CO2, we just decided, is nonpolar. And so one CO2 molecule to the next CO2 molecule, they're not really attracted to each other. They just kind of pass by and like, yeah, whatever. Who cares? You're there. And if you want to separate them, you're like, hey, can you guys separate? They're like, sure, whatever. It doesn't take much energy. And so we boil CO2 at a very, very low temperature, right? Even at room temperature, CO2 is boiling. It's above, right? It's a gas. And so these properties really affect how things go. You want to know why molecules and certain drugs attack certain areas and why some are soluble and why some aren't? It has to do with all this shape, this geometry, this polarization. And you get some really cool things going out of it. So I think I've gone long enough. Those are our 3 videos. That's most of what you need to know for Chapter 6. And if you have any questions, just let me know.